Hey, hello and welcome back everybody. This section is called Inner Products, Norms, and Orthogonality. And inner products are actually one of the more important topics of linear algebra and quantum mechanics. Really, inner products give us a whole lot of information about all sorts of different mathematical objects. Always vectors, but very abstract vectors when it comes to quantum mechanics. Just these notions of quantum states. The fact that you can perform an inner product to extract terms is kind of what all of quantum mechanics is based off of. So we will start there, and then the other two are kind of just consequences, both norms and orthogonality, at least with respect to finite dimensional vector spaces and or Hilbert spaces, which are kind of these infinite dimensional ones. Norms and orthogonality are kind of consequences of inner products. So we'll start with inner products and really hammer those in before we get to the other two. So inner products. An inner product of two vectors with basis representations or vector representations let's say C1, C2, C3. You use the dot symbol between them. D1, D2, D3 is equal to C1, D1 conjugate. So this is that complex conjugate coming back. And if you don't remember what that is, you replace I with negative I. So every time you see I, you replace it with negative I. Plus C2, D2 conjugate, plus C3, D3 conjugate. This would be in 3 dimensions. So that's just the inner product for 3-dimensional vectors. And we also have the notation given by an angled bracket. So we could do something like C1, C2, C3, comma, D1, D2, D3, angled bracket. And this is the same. And actually in quantum mechanics, they do the same sort of thing, but instead of putting a comma in the middle of the angled brackets, they put an entire stroke. So these are all the same representations of something called the inner product, and that's the specific case of 3 dimensions. To try to make it a little bit clearer before I jump into arbitrary dimension, let's run one example. 1, 2 minus I, 2, inner product, negative I, 4 plus I, 3. What I have to do is identify just straight across, right? The idea is the C1, D1 is just straight across, plus C2, D2, which is just straight across again, plus C3, D3, which is just straight across again, and I just have to keep in mind that each of the D's come along with complex conjugates. So all I'm doing is I'm looking straight across, and I multiply these two terms, and I'm taking a complex conjugate on that side. This will be 1 times the conjugate of negative I, plus, and I'm going to go right across again, 2 minus I times the conjugate of 4 plus I. And then finally, I'm going to add one more case, which is adding 2 times the conjugate of 3. If I want to simplify this, the conjugate of I, I'm going to replace every I with a minus I. So negative I is a positive I. I'm going to replace every I with a minus I, 4 minus I, and I'm going to replace every I with a minus I. There were no i's there, so I don't have to replace anything, and I still have 3. So what I'm left with is 1 times I plus 2 minus I times 4 minus I. And I can FOIL that out, plus 6. So if I go ahead and FOIL this out, I end up with 8, that's 2 times 4, minus 2i, that's the outside, minus 4i is the inside, and the last is plus I squared. I squared is negative 1. I'm going to have 8 minus 1 is going to give me 7. Minus 2i minus 4i is minus 6i. everything in the middle turned into 7 minus 6i. If I decide to do I minus 6i, I'll have a negative 5i, and I'll have plus 6 plus 7, I'll have 13. So it turns out the inner product of these two vectors was 13 minus 5i. This should always be a complex or real number. You should never end up with a vector after an inner product. That's a very common mistake students will make. For some reason, they do something incorrectly and end up with a vector after taking an inner product. You should never end up with a vector after taking an inner product. Let's look at the arbitrary case, because we just did an example in one situation, in the three-dimensional situation. The generic inner product of two sequences. Let's say my first sequence is C sub k, and k is just in an index set for my sequence, and D sub k, where k is also in that index set, is defined by, and I'll use the angle bracket here, ck, k is in my index set, dk, k is in my index set. It's going to be C superscript k conjugate D subscript k. That way we can use Einstein's summation to recover our answer. And so this may be the sum over all k in the index set of ck and then the conjugate of dk. So that's the generic inner product of two sequences. You'll notice that what was happening above with two vectors is you can think about the vectors as sequences with just the index set 1, 2, 3. That's my index set 1, 2, and 3, 1, 2, and 3. And then my inner product is the sum k in the index set 1, 2, 3, C sub k conjugate D sub k. So that's where the three-dimensional version came from. It really is a version of this more general form. And the general form needs to be quantified even more because we can encounter cases like the following where I have functions. So let's do a function. Maybe x is in the index set 0, 1, and g of x, where x is in the index set 0, 1. We should keep in mind I talked about how to perform the Einstein summation over continuous index sets. We no longer really have a sum when we perform Einstein summation. When we perform Einstein summation, we now have an integral over the index set. So really think about these as functions, and we take the complex conjugate of the second function. And so what we learned down here is that the inner product of functions are integrals, but the inner product of vectors or maybe other sequences with discrete index sets are going to be summations. So inner products are either summations or integrals, depending on if we're working with functions or sequences or vectors, kind of finite dimensional vectors. So let's just do a couple more examples of these. So let's do an example. Let's take the inner product of 1, 2 minus I with 2 plus I and 1. You're going to see me use the bracket notation the most often. This is the most mathematical notation of all of them. However, you should keep in mind the other notations as well. But let's take this inner product, and what do we get? We get 1 times, so I'm just looking horizontally across here. I'm going to multiply and give a complex conjugate to the second term. So we'll go complex conjugate of 2 plus I, plus I'm going to go horizontally again and give a complex conjugate to the second term. We will have 2 minus I times 1 with a complex conjugate on it. And the output here then will be 1 times 2 minus I plus 1 times 2 minus I. We're going to recover 4 minus 2I. But let's do another one. Let's do the function. Let's say that I have a function f of x equals x squared plus 1 and g of x equals ix minus 2 over the domain 0 to 2. Then I can take an inner product of f against g, and I end up with the integral from 0 to 2 of f, which is x squared plus 1, times the conjugate of g. The conjugate of g was ix minus 2 dx. And if I FOIL everything out from these two terms multiplied together, it looks like I have my first gives me negative I x cubed, the negative coming from the conjugate. My outside gives me negative 2x squared. My inside gives me ix, and my last terms give me minus 2 dx. And if I wanted to integrate that, I can use my power rule in each term. I is just a constant, so x to the fourth over 4 minus 2x cubed over 3 plus, I forgot, there's still a conjugate, so that should be a minus sign from the conjugate. So both of these are from the conjugate. So it should actually be a minus here. Minus ix squared over 2 minus 2x, and then I evaluate on my bounds 0 to 2. If I plug in a 2, I get 2 to the fourth over 4, which is 16 over 4, also known as 4. So I have a negative 4i. I plug in a 2 for the x cubed, I get 8 thirds, times 2, I get 16 thirds. Plug in a 2 for the x squared, it's 4 divided by 2, I get 2i. And then I plug in another 2 into the x, and I get minus 4. So that's me plugging the 2 in. Then you subtract, plugging a 0 in, which gives me 0, minus 0, minus 0, minus 0. Thankfully, the 0 terms don't matter too much, but I can combine the like terms to put myself in normal form. 4, by the way, is 12 thirds, so I'll have negative 28 thirds is my real part, minus 6i is my imaginary part. So that's how I can take an inner product of two functions. As long as somebody tells me the domain, I want to be clear that that's where I start and I stop all of my integrals. Okay, so now that we've established inner products, maybe let's establish a few properties of inner products. So there's something called bilinearity, and technically these are conjugate bilinearity. And what this means is, suppose that I start with a linear combination of two vectors on the left-hand side of an inner product, and I just have another single vector on the right-hand side. Then what bilinearity allows me to do is it allows me to distribute all terms of the inner product the way we would think we should. Because in some sense, the only terms that the inner product should be interacting with are the two vectors on the left along with the one vector on the right. So those constants a and b shouldn't matter, as well as the plus sign. So the bilinearity allows me to get rid of all of those. Well, it allows me to move things around. But where does the conjugate come from? The conjugate comes from the fact that the right-hand side is going to give me a complex conjugate. So if I do something like a w1 plus b w2, then this actually, the a pulls out, but it pulls out as a complex conjugate. So I have some sort of distribution that occurs, but it doesn't quite occur as I would want it to in the second entry. It needs to occur as a complex conjugate in the second entry. So you can pull everything out, but you have to make sure that you pull things out correctly in the second entry. We also have something called antisymmetry, which is where we have that the inner product of two vectors v and w is conjugate to me trading their places, w and v. So symmetry would be flipping them around and recovering what I started with. Antisymmetry, we have a complex conjugate on the right-hand side. And the last property is called positive definiteness. In this property, we'll set up the next idea we're going to talk about, which is the norm. But the idea here is that if I take a vector and I give itself the term that I want to take an inner product with, this is always greater than or equal to 0. And in fact, it's equal to 0 only when the vector v had only zeros as coefficients. So only zeros as coefficients. So the 0 vector is the vector with all zeros in the coefficients. So you only recover that this inner product reaches 0 when all of the coefficients are 0. So let's go ahead and use at least one of these properties right now. Actually, let's go ahead and use at least two of them. So let's consider the following. So I'm going to consider 3 times the vector 1i plus I times the vector 1, 1. And I'm going to take the inner product with itself. 3 times the vector 1i plus I times the vector 1, 1. So I've put a linear combination in for both sides here. And what I can get away with is a sort of foiling. I can get away with a sort of foiling from this idea of bilinearity. The idea of foiling, what do we mean by foiling, is I look at my first, and I'm going to write those down as 3, 1i, 3, 1i. I'm going to look at the outside, which is these two. I'm going to say this is 3, 1i, I, 1, 1. I'm going to look at the inside, which is I, 1, 1, and 3, 1, I, and I'm going to look at the last terms, I, 1, 1, and I, 1, 1. So bilinearity, not only does it let me foil like that, but actually bilinearity now gives me the ability to pull the numbers out front. But since this one occurred on the right-hand side, we gain a conjugate. Technically, that 3 gains a conjugate. The I does not gain a conjugate because it's on the left. The 3 gains a conjugate. And then the I does not gain a conjugate, and then the one on the right does. And what does this give me? Well, it gives me 3 times 3, so it gives me 9 on the first case. 1i, 1i. Then I end up with 3 times the conjugate of I, so that's going to be negative 3i. And then I have 1i, 1, 1. Then I end up with 3i, because there's no conjugate on the I there. 1, 1. 1i. And then I end up with I times negative I, because the I gains a conjugate. I times negative I is negative I squared, also known as negative negative 1 or positive 1. So now I just have 1, 1, 1, 1. Now I'm able to just compute. This made my life a little easier. I just have to compute these. But I can get away with something even easier than that, because actually these two will be conjugates by anti-symmetry above. So I really only have to compute 3 of those regular inner products. So let's go ahead and compute those 3 inner products. Here I'm looking horizontally. I have 1 times 1. That's 1 squared, also known as 1. And here I have I times negative I, because there's a conjugate on the second term. I times negative I, negative, negative 1, also known as 1. So that term's giving me 2. This term, if I look on the top, I get a 1 squared, which is 1. Then I get an I on the bottom term. And I know that the latter one's going to be the conjugate of what I just drew because of anti-symmetry, so I have to have 1 minus I. And then in this last case, I'm just going to have 1 squared plus 1 squared, which is 2 again. So what I end up with is 9 times 2 minus 3i times 1 plus I plus 3i times 1 minus I plus 2 times 1. If I expand everything out, I can distribute my 3 i's across. I have 18 minus 3i. Minus 3i times I will give me a plus 3. Then I have plus 3i. Minus 3i times I will give me a plus 3. Plus 2. You'll notice that positive 3i and negative 3i cancel. This is guaranteed by positive definiteness, since left and right were the same in the first case. And so what I'm left with is 18 plus 2 plus 3. I'm left with 23. So that's one way of using all of these nice properties to make my life a little bit easier when computing inner products. So let's go ahead and get to the last 2 definitions that I wanted to introduce. We have this idea of a norm. So a norm, maybe I'll make a double line here. A norm of a vector, and actually it's not a norm, it's the norm, is the square root of the inner product of the vector with itself. And in fact, a norm has a notation. Maybe I'll write the notation here. I'm going to place two vertical strokes on either side of a vector, but it's also common to just use single vertical strokes. Either one is fine. And we're going to give it as the square root of the inner product of the vector with itself. So this norm of v will be the square root of the inner product of v with itself. And they represent the quote-unquote distance from the zero vector. So the vector with all zero components in it. The norm represents the distance from that point. Let's just compute one example. Maybe we'll compute two examples. The norm of the vector 1i negative 2 equals the square root of the inner product of the vector with itself, 1i negative 2. And what is that? Well, we're going to look horizontally across. 1 times 1 is 1. I times negative I, because the complex conjugate, is negative 1, so plus 1. And then we have negative 2 times negative 2 is going to give me a 4. 1 plus 1 plus 4 is 6. The norm of this vector is root 6. Another example, we can work with functions even. Let's do x on the domain negative 1 to 1 is, so its norm is going to be square root of the inner product of f with itself. And let's recall that inner products of functions on domains are the integrals over that domain. So we have an integral from negative 1 to 1 of the function f, which was x dx. We compute this as x cubed over 3 from negative 1 to 1, which will give me the square root of 1 cubed over 3, which is 1/3, minus negative 1 cubed, which is negative 1 over 3, also known as the square root of 2/3. So we can actually compute norms of functions as well using this definition. Finally, we'll talk about orthogonality, and this is pretty straightforward too. We consider two vectors to be orthogonal if the inner product of the two vectors is 0. And maybe I'll say that we consider the two vectors, v and w, to be orthogonal if the inner product between the two is 0. And so that's just a name that we give to these vectors that we call orthogonal. So let's look at examples of these. We can do a couple examples. Let's say the vectors 1, I, and I1 are orthogonal, since, let's look at the inner product here. 1, I1. We go ahead and read across horizontally. We get 1 times negative I because of the complex conjugate, so I get negative I. Then we read horizontally again, we get I times 1 plus I, and what do we end up with? It's a big old 0. It turns out functions can also be orthogonal. We can look at f of x being sine pi x, and g of x being sine 2 pi x over the domain 0 to 1. By testing, the inner product of f against g is going to be the integral 0 to 1 of sine pi x against sine 2 pi x dx. And you maybe don't know how to take the antiderivatives of these right now, but let's recall once again the double angle formula. Double angle for sine, you have sine of 2 theta is equal to 2 cosine theta sine theta. Here theta happens to be pi x. So every time we see those, we're going to plug in a pi x. This will be equal to 0 to 1 sine pi x times the double angle formula, which was 2 cosine pi x sine pi x dx, which is the integral 0 to 1. It's twice the integral 0 to 1 of sine squared pi x cosine pi x. And I realize this is maybe a real throwback for everybody. This can be some u substitution if I let cosine be du and sine be u, this happens to be twice the integral of u squared du, because the derivative of sine is cosine. So this is twice u cubed over 3, or in other words, 2/3 sine cubed, because u and sine are the same, pi x. Evaluated on my bounds, 0 and 1, I get 2/3 sine at pi minus 2/3 sine at 0. And if you don't believe me, let's recall the unit circle. I move around by pi, I end up here. Sine is the y value, y equals 0. So that's 2/3 times 0. And the sine is the y value here, minus 2/3 times 0. And I get 0 as my answer. So the fact that I got 0 as my answer of an inner product means f and g are orthogonal. So we're going to stop there for today. We'll get a lot more practice talking about these ideas of inner products, orthogonality, and norms in the worked example section. I'll see you then. Bye.